I would like to start the last session, and I would like to thank you all for surviving so far. As mentioned earlier, this is probably not the most fun that you had during your stay in Israel, so I would like to apologize for that. Wait till you fly out, then you will find out. But in any case, there is something that both Ellie and I did not explicitly say, and I think it should be said. We told you that we need to break the system faster than exhaustive search. And we didn't mention it, well, we didn't have much time, but it has to be said clearly, that the reason we discuss generic attacks, these are the baselines. Any cipher, it doesn't matter if this would have had different P permutation or E permutation, or instead of 16 rounds, 1,000 rounds, 1 million rounds, exhaustive key search would still be applicable. So these generic attacks set a sort of benchmark. You need to be better than exhaustive search or the table attack or Hellman attack, even though Hellman was never used as a real benchmark, to be considered as a break of the cipher. Now, I'm not going to enter the discussion what a break is. Even people doing cryptanalysis on a daily basis, we still haven't really agreed what we mean when we say that something is broken. Long story. Even people dealing with real numbers have issues, not only people doing asymptotics. But in any case, if the attack, generally speaking, if it takes less time than exhaustive key search, we treat it as some security issue. It might be an attack which, like differential, takes 2 to the 47 rather than 2 to the 56. And you can say, well, 2 to the 56 in exhaustive key search, I can do it in my garage or with my Copacabana or with my systems. In differential, I need 2 to the 47 data. But it's some sort of a dent in the armor. I mean, look, block ciphers or any real primitive at the end, unfortunately, there are no real security proofs. I'm terribly sorry for those of you doing security proofs. I'm talking about things which are not one-time pad, in the sense that you have security reductions. But nobody really knows what the complexity of breaking RSA is. We conjecture that the best known attack is factoring and generalized number field sieve under these parameters. We conjecture that the best known attack against DES is linear cryptanalysis of this variance that takes 2 to the 41 chosen plaintext. We conjecture, we cannot prove that. And the reason people are using DES or AES or any other cipher in their constructions is because people like us, cryptanalysis, never mind, look into these schemes and try to break them in as crazy model as possible. And we get this warm, fuzzy feeling of security if even after a lengthy period of time, assuming the craziest notions of security, when you discuss block cipher and encryption, you can say, well, only non-plaintext is an issue. Only attacks which are based on non-plaintext are an issue, because in real life, who gives you chosen plaintext capability? Or adaptive chosen plaintext and ciphertext capability? Those dealing with public key crypto systems don't see any problem with that, because, well, the model is different. But with secret key, how dare you ask for chosen plaintexts? Well, there are models which allow that. There are actually historical examples, and today, for example, if I send you an email encrypted to your Gmail account, and you access it using SSL, the SSL connection encrypts data that I chose as an adversary. So the chosen plaintext model is reasonable. The adaptive chosen plaintext and ciphertext is slightly less reasonable, but again, I can do various things with it. BGP? For example, BGP, but also again, I can use the same Gmail example. And the crazier the model is, we would still hope that the primitive is secure. And the reason for that is to have this warm, fuzzy feeling. Everything is fine. We gave the adversary everything. Huge amounts of data, huge amounts of memory, assuming that accessing memory takes order of 1 encryption, which is not always the case. We gave him whatever he asked for, and he still couldn't break the scheme. So this brings me to the related key attacks, which are actually yet another crazy model, though not as crazy as it used to be. And Kanye is going to discuss this a bit tomorrow. So I remind you, we have this block cipher, and all of the attacks that we discussed so far actually try to attack this E by controlling the input or the output or both of them of the encryption algorithm, of the block cipher, of the ES or AES. Now, the related key attacks that were introduced independently by Knudsen and by Biham at 93, the adversary gets to control the key. Nobody complains, your spirit is broken. Nobody cares at this point. Just a second. The entire field of cryptanalysis is, let's try to find the key faster than exhaustive key search. If you shave one single bit of the time complexity required to do the attack, you broke the scheme. And now I'm allowing you to choose the key. What's the point? I accept suspicion. Thank you. So this is actually a very strong notion. If you're choosing the key, what you can attack with. So the model is slightly different. What you do, there is some unknown key which I don't know. You control the key. Now, let's assume you're running a chosen plaintext model. Can you please encrypt me this plaintext under the key that I don't know? Okay? Thank you very much. Now, for this magic, I would like to ask you to flip bit number 8 of the key, which I don't know, and encrypt this plaintext. Now take this plaintext and encrypt it under the key where you flipped bit 9. Now, of course, the more control you give to the adversary, like flip more bits or compute more complicated functions, the attack seems less and less realistic. And of course, there are several relations that I would like to exclude. For example, if I tell you, okay, can you please encrypt this plaintext under the key that I don't know? Now take the key that I don't know and set the first bit to be 0. And now encrypt the same plaintext under the key that I don't know. If the first bit of the original key was 0, then the encryptions of the same plaintext under two different keys would be the same. So there is also a question about what are the correct relations, and I will have to cite the US Supreme Court that said that valid relations are like pornography. I cannot define it, but I will tell you when I will see it. Meaning, if it's XOR or rotations or any of these things, I would accept this as a valid relation. Of course, you can build, if you have XOR and 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 addition, you have the AND operation. If you have the AND operation, then you can again find the key very quickly. Now, the thing is, when people started discussing related key attacks, people said, well, you know, who gives you the right to flip bits of the key? But then there are protocols, for example, web, that actually allow you to have related key capabilities. And if this is not enough, if you're working with the block cipher in a compression function, so hash functions use compression functions, they're using the block cipher in some mode of operation, for example, Davis-Mayer, and then the message block that you hash, that you compress, is used as the key to the function. And you would like the block cipher to be secure so that we could just take one block cipher, put it inside Davis-Mayer, and use it. And then the adversary has control not over the plaintext, but over the key. And I would like to know what happens to the security of this construction. And besides, sometimes we have very strong relations. So strong relations that despite the fact that the name of the attack is related key attack, I just need access to the encryption under one single key. So the relations are so strong. So I would like to introduce to you this again. This is the key schedule of the ES. C, D, rotate left, rotate left. And at this point of time, if you remember from this morning, by chance, the sum of the rotations is 28. And there is a bit of an issue if you're an engineer who wants to implement this thing. The first round is rotation by 1, then rotation by 1, then by 2, then by 1. But you need to store some sort of a table. You have some You need to use maxes to implement this thing. You need tables. It complicates life. Here is a solution. Let's make all the rotations the same. Let's say by 7, by 14, by 21 bits to the left, which will reduce the amount of gates that we need for the implementation. And after 16 rounds, the rotations will be, again, after a multiple of 28, so the registers will be ready for encryption again. Those who think this is a good idea, please raise your hands. Those who think it's a bad idea, please raise your hands. Those of you who are too tired to raise your hands, please blink twice so I know that you're still awake. Okay. So it's a bad idea. I'll show you in a second. Now, this has a very interesting property, and now you'll have to read everything the other way around. This is Israel, so this is from right to left. In Israel, this is from left to right. So I'd like to ask you the following question. What happens if I complement the key? Well, if you complement the key, look very carefully at this key schedule algorithm. If I negate all the bits of k, I negated all the bits of c and d. Which means that I negated all the bits here and here, which means that PC2, if I look at one key and the complemented key, the negated key, the values are just going to be one, the complement of the other. These are just pick bit number 1 of the key, bit number 5 of the key. So if you flip the value of bit number 1, nothing will change. Well, everything will be flipped actually. So if you start with k, with some key k, all the subkeys are going to be k1 to k16, and k0 will give you k1 to k16, all of them not. Now, what happens if I also complement the input to the round function? In this case, well, let's see. And the E permutation just duplicates bits. What happens when you duplicate a negated bit? You get a negated duplication. So if I had L here and the expansion of L here, now I have the complement of L and the expansion of the complement, which is the complement of the expansion. You'll have to trust me that this is how linear functions work. But what happens when you XOR the complement of the expanded L with the complement of the key?
The same as before.
The complementation disappears. Meaning that I'm going to get the same input to the S boxes, meaning also the same output from the S boxes, meaning the same output from the P permutation. And if I also negated the right-hand side, that means that at the end of this round, I will have negation here, and this property propagates to the next round, where also the subkey has been negated. And this is the complementation property of DES, which actually says that if you encrypt P under K, and you encrypt P naught under K naught, you will get the naught of the encryption. Of course, if this was a pseudo-random permutation, this would be a very simple distinguisher. But I guess that by now that you know, given that the description of this is actually quite compact, this is not a pseudo-random permutation, so who cares? Who cares? Okay, we have a few people who are still...
No, but the function is that it's pseudo-random if case fixed, not if you play with case.
This is also a problem of the definition that indeed the relations of related key to how you define PRP is not very... they were explored but not satisfactory. In any case, this property allows me to do an exhaustive key search against DES using 2 chosen plaintexts in half the time. Only 2 to the 55 operations, and the idea is follows. You ask for the encryption of P and P naught, and you obtain C1 and C2. Now, I will do exhaustive key search, fixing the first bit, the most significant bit, to 0. I compute a trial encryption. If the encryption of P under the key that I'm checking is equal to C1, I think it's obvious that the key is K that I'm checking at the moment. The question, what happens if by any chance I took this,
No.
What happens when I actually try to encrypt not with the right key, but the complement of the key? So in this situation, this is not the right key. The correct key, we'll use it, let's say, K prime. I'm using the negation of K. What will happen when I will encrypt the negation of, I will encrypt P with the negation of K? Well, we have from the complementation property that this is equal to K not not, P not, everything not. So this is the trial encryption that I'm computing. Well, not or not is this. And this looks suspiciously like C2. Meaning, if during your trial encryption you find out that you actually received the negation of C2, then it's very likely that the key that you're looking for is the negation of the key that you're trying. Okay? So this is a problem in the cipher, a real problem. And what it tells us, that there are actually related key issues here.
But didn't you have a, sorry,
Yeah.
isn't there a problem with this is the negation of P, and there was,
You negate everything.
but here you don't negate P.
I don't negate P, but the thing is that in the encryption, C2 is the encryption under the negated. The negation is hidden somewhere. Okay. So now let's go back to this variant that says let's have all the rotations being the same. Okay, what's the problem? Well, consider, for example, two keys, K and K prime, such that K prime is actually, so the key is loaded into registers C and D, and after one rotation, we get the same situation that we would got if we put in K. Meaning, we initialize the key schedule algorithm twice, once with K prime and once with K. When we initialize with K prime, so there is the first round, we rotate the registers C and D, and you reach the same state as we got just after initializing with K. So C prime and D prime are equal to C and D. Now, if the number of rotations is always the same, that means that the state of C and D is going to evolve together. If these are equal, these are going to be equal, these are going to be equal, these are going to be equal, these are going. All of the subkeys are also going to be equal, because the state of the key schedule algorithm of register C and D is the same. And the subkeys just pick bits that and that from C and D. Meaning, I will get these 15 subkeys to be the same, and here the 16th subkey, well, you see there is a shift by 1 in the encryption. Who thinks it's a good idea? Okay, obviously not. So now let's assume that I take a plaintext P prime and I encrypt it, and this is a general thing, but now let's assume it's this, so I encrypt it one round under K1 prime, and let's assume that I got a value here, P. This is after one round, and at the end we get C prime. Now, what will happen if I will try to encrypt P under K? If I will try to encrypt P under K, look, this is the same subkey. That means that the value here is the same. This is the same subkey, same input, same output, same subkey, same input, same output, all the way here. Meaning that here I'm going to get C prime. There's only one round difference between C prime and C. Now, one small comment, even if the number of rounds was 1 trillion, zillion, whatever, this property of actually having two plaintexts which are just shift by one, the encryption one of the other, would maintain, would be preserved. And now, something, we didn't mention it, but you have to trust me that if I'm giving you the input for one round of DES, the input and the output, and the input and the output, this is one round of this, finding the key is very simple. Very, very simple. So, if I will succeed to find two keys that satisfy this relation, and I will be able to find two plaintexts that satisfy this relation, I broke this. Well, it's a modified version of this. This is not really this. So how do we do that? Okay. Because this is a facial structure, encryption by one round, what happens in the encryption of the first round? Let's say that we have plaintext left and plaintext right, and we have here plaintext right tag and plaintext left tag. This is the situation that we are looking for. Now, if you look very carefully, you will see that actually this PL prime became PR with no change. Now, if I had known the first subkey, it would be very easy to find the relation between PL and PR prime. But if I know the key, then there is no point in running any attack, right? So let's assume that I don't know the key. So we'll just use the birthday paradox. It's a very useful paradox as an adversary. Take 2 to the 16 random values here. Take 2 to the 16 random values here. So you fix this side. Oops. That should be. Fix the value of PR. Take 2 to the 16 values here, 2 to the 16 values here. By birthday arguments, you expect them to have a pair that satisfy this relation. And it would be very easy to find this pair, because if you go to the ciphertext side, there are 32 bits which just went from one side to the other. So it's very easy to identify this pair. And if I find the pair, well, if I have the pair, I actually have the inputs and the outputs of the first round, and the inputs and the outputs of the last round. And again, take my word for it, it's very easy to break this. One round of this. Now, complexity 2 to the 16, data 2 to the 16 time, and just you throw everything at the end into a hash table to find the pair. Concept is clear. The best that it can be this time, okay, right? Feel free to complain. One small rant. We don't have a good name for this pair. Related key plaintext pair is the best name we came up with. Not a very decent name, so we're looking for names. Okay, I just want to stress the point that the encryptions are under two related keys that I need the ability to pick. It's not. I'm not going to defend the model. This is the model. I need this ability, but with this ability, I can break any number of rounds of DES, assuming that the subkeys are the same.
Does it work also for the regional rotations?
No, because the different rotation constants make sure that this property doesn't happen.
Okay, but does your attack extend?
No, because the registers will not be aligned correctly. Even after one round, they will evolve the same way. This one will be rotated by 2, and this one will be rotated by 1. After, in the second round and the third round, the rotation constants are different. So one will be rotated by 2, one will be rotated by 1. So even if the keys were the same before, they will be different after. So the subkeys are different, so the data path, the encryption data path is different. Now, I will go very quickly over the second attack, which actually needs access only to a single key. Earlier, I assumed that I have the ability to choose the relation. Now, let's assume for a second that I don't have this ability, but I still have the property that all the subkeys are just shift one of the other. Let's assume I pick a plaintext. PLPR, and I ask for its encryption. Then I ask for the encryption of all the plaintext of the form PL prime and all possible values here. Now, my claim is the following. When I partially encrypt this plaintext under the key K, if by any chance the key that I encrypted here is the correct key, the trial encryption would work. If by any chance the key that I encrypted here is not the correct key, but the correct key shifted by one round forward, meaning the correct key starts with, I'm checking here K1, K2, up to K16. However, the correct key had the sequence, generated the sequence K0, K1, up to K15. In this situation, what happened is I encrypted this plaintext one extra round. But in this one extra round of encryption, what happened? This plaintext is the partial encryption of one of these values by one round. So I took one of these values by accident, encrypted it one round extra. So if it's one round extra, there are 32 bits which just go without any change. So I will be able to find them. I will be able to look at the data and say, you see here, this is CL and CR. CR is the true ciphertext here of one of these values, which means that there's a good chance that actually the real key is shifted by one round. We'll let it sink for a second. It's where you usually lose the paper. Don't worry. I also, all the time, have to read it twice. So the idea is, I actually try to find this related key plaintext pair using a single key. So what I do, I try one key and I hope that the data contains the plaintext pair, the other value, by accident. Or, well, actually I forced it to exist there by taking all possible values here. So by trial encryption of one key, I also try the key which is shift of one key, one round backwards. Now, taking all the plaintext of the form of this form, this trial encryption also allows me to check whether if by accident I got the key to the other side as well.
It's very similar to what you did with complementation, right?
Very similar, yes. The complementation adds. So this is why, if you look very carefully, in some places, all the things in green are actually you can do this along with the complementation. What we actually found is a relation between the encryption of this plaintext under this key, of the related plaintext under key, which is rotation one round backwards, one round forward, and the complementations. So a single encryption allows you to check 6 keys. Now, I'm not going to do all the bookkeeping. I will let you read it at your free time. So you will have to trust me that using this method, you can actually check in one encryption 6 keys, which means that, on general, the time that it takes to do exhaustive key search was reduced by a factor of 6 compared to exhaustive search, or by a factor of 3 in comparison with using only the complementation property. There are some small technicalities here because there are some cycles and
maybe there is another game, additional game that you don't need the Oracle to give you really pure Oracle accesses.
So the thing is, for the amount of data that I need has increased to 2 to the 34. the amount of computation was reduced. So there is a trade-off here between these solutions. Okay. Those of you who I lost, it's time to come back. Slide attack. It's exactly the same attack, but when you don't need related keys, but a single key. So assume for a second that the key schedule is such that all the subkeys are the same. Okay, you get the same subkey again and again and again and again and again. And this is the same permutation, same key permutation again and again and again and again and again. Million times. The same attack works. If I succeed to find two plaintexts such that the encryption of one of them is a shift by one of the other one, this property will exist also in the ciphertext side. And now, instead of dealing with these million rounds, all I have to do is take P prime and P, C prime and C, and attack one round of the encryption. Now, I can say, here is a very good solution to protect ourselves against these sort of attacks. Let's make the round function very, very complicated. Let's say a random permutation, a truly random permutation. However, as you've seen in this, the round function has to be implementable. You cannot put here huge tables. So we are constrained to some sort of reduced random permutations. They're not truly random. One round of encryption usually doesn't give you much. We add more rounds to make sure that the probability of all differentials goes down. We add more rounds to make sure that all linear attacks takes more time. We add more rounds so meet-in-the-middle attacks will not happen. But here we're independent in the number of rounds, meaning you cannot use the same permutation and the same subkeys. So there are two solutions to the problem. First of all, making sure that not all subkeys are the same. And the second one is just having a small changes in the function. For example, you XOR a round constant or you add a round constant. Yes?
Maybe it's the late hour, but could you explain again how this attack works? I mean, you know P prime, but how do you know P?
I take 2 to the, let's say, the block size is, let's say this is des. And we have a modification of des called des to k. First round you use 48 bits of key as k1, second round k2, 48 bits. Then k1, k2, k1, k2, k2. 96 bits of key. Million rounds. No differential cryptanalysis. Everybody are happy? No differential cryptanalysis? You can forget the previous talk. Can you break it? And the answer is yes. Take this round function to be actually 2 rounds of DES. Breaking 2 rounds is very easy. So here is a simple attack. Take 2 to the 32 random plaintext P. On average, you expect, due to the birthday paradox, to find a pair. This is called the slit pair. Luckily, we have a name for that. Such that P prime is the encryption, such that P is the encryption by 1 round, which are 2 real rounds of DS, of P prime.
What is P? What is P?
A plaintext. You take 2 to the 32 plaintexts. P1, 2, 3, 4.
Yeah.
2 of them, by birthday arguments, will satisfy this relation.
That one of them will be the
The-
one
yes.
of the other. Okay.
So I will go over all the possible 2 to the 64 pairs. And for each of them I get P prime was encrypted to P, C prime was encrypted to C. You will have to trust me that the attack scenario in this time is 1 step to find the key. So I reduced the time complexity, reduced actually, by the way, I'm not giving any credits to all the work that was done. This is by Wagner and Biryoko from 1999. So the attack finds the key in 2 to the 64 instead of 2 to the 96. And there are other improvements. So we would expect million rounds of DS to be secure. Okay, so how do you find the slit pairs? Because once you have the slit pair, you apply the attack that takes 1 clock cycle, 1 encryption. It's very simple. You take all the possible pairs. For each pair, you run the attack. You see if you get out of the attack a consistent key, a correct key. And if it's a correct key, you found a split pair. But the only reason we're interested in finding split pairs is because we want to find the key. If you're giving me the key without split pairs, I don't care. I mean, the game here is find the key, not find split pairs. So actually, we have a bit of a problem here, and you try to find all possible pairs. There are several techniques that try to find the keys, the split pairs, not by take all possible split pairs and see which of them works. Okay, so we said that. Now, in the case of a faceless structure, instead of a non-plaintext variant, we can reduce the data complexity to a chosen plaintext one, and same trick we just seen here with this. You fix one half on one side, and you reduce the spaces. Okay, here's another cool slide attack, the complementation slide. Again, 2K des. Here we have PI, PJ. You can see that the encryption is XOR with K1, XOR K2, K1, K2. And you have here this wonderful, completely random permutation. If you really insist, this is based on RSA. Just pick the random permutation that you like. Okay, and I'm looking for PI and PJ, that by chance, the encryption here, after one round, is XOR with delta. This value XOR this one is delta, this one is XOR this one is delta, such that delta is the difference between K1 and K2. Now, if this is the case, what will happen is, here I have RJ XOR delta. It is XORed with K2. The thing is that this value is actually RJ XOR K1 XOR K2 XOR K2. So a bit of hand waving, and you find out that actually this is the same input here. Same input here, same output here, meaning that this delta difference remains, and the process repeats. So if you start with two values such that there is a difference delta here at this point, you're sure to have at the end of the encryption again this property. This is an assertion that remains. And from this point onward, the attacks are very standard. Look for a split pair that satisfies this and this condition. Take the split pair, try to break the cipher using the split pair because you have to attack only one round of the cipher. Actually, I have to give a small comment. The attack doesn't really work in the case of DES because in some cases the delta does not satisfy the expansion function of DES. Technicality, I think at this point of time we're not going to discuss any more technicalities. Slide attack with a twist. And is anyone who's doing yoga, Pilates, any of these things? So the idea here, again, 2K. The idea is as follows. Let's try to find relations between encryption and decryption. So one encryption is looked upon upside down, the other one looks the right direction. But roughly the same. Let's assume when you encrypt PI, you get these two values, and when you decrypt PJ, it's the same value here. So the ciphertext that goes with this plaintext is related to the one round before the end of decryption of this ciphertext. So the idea is to switch the order. And again, all the techniques, given 2 to the 32 non-plaintext, it's very easy to find the key. And I just want to mention that you can combine slide with a twist and complementation, slide with complementation, and using these two techniques you can break DES 4K, which is the cipher where you encrypt 4 rounds of DES, K1, K2, K3, K4, K1, K2, K3, K4. All of them are independent of each other. Data complexity 2 to the 32, same standard attacks. It works. Okay, so now back to some theoretical construction, the Evan-Mansour construction. This is a random permutation, publicly accessible. And if I'm giving you one random permutation and you want to construct a block cipher out of it, there is a very elegant solution by Evan and Mansour, which is the Evan-Mansour block cipher. You XOR one key to the plaintext, you throw it through the random permutation, then you XOR K2, and you get the ciphertext. Very simple. 2 XORs and a random permutation. And if the block size is n bits and the key size is 2n bits, and this is the encryption function, there are actually security proofs that shows that the total number of queries to this random permutation that the adversary has to make, and the total number of data points, pairs of plaintext and ciphertext that he needs to find is actually 2 to the n. Their multiplication is 2 to the n. And there's actually a very simple attack with 2 plaintext and ciphertext that finds the key. There's actually also a differential attack by Damen that meets this security bound, but it's a chosen plaintext attack. And there's a slide with a twist attack that uses 2 to the n over 2 known plaintexts and time. So here is the attack. You ask for the encryption of 2 to the n over 2 values, p and p and p star, and you look for pairs such that the difference between p and p star happens to be k1. If this is the case, p becomes p star, and p star becomes p after the addition of the first key. Okay, so now p goes through the f, p goes through f, and now we have XOR with k2. And you can ask yourself, why do I care? And the thing is, if C is equal to encryption, the permutation of, the permutation of P star XOR K2 and C star is the permutation of P XOR K2, when you XOR the two of them together, you will find out that C XOR C star is actually the XOR of the outputs at this location. Now, this is still a very annoying relation that you need to check. Everybody agree that this happens? That if indeed P became P star after the addition with K1 and P star became P after the addition with K1, this relation holds. And you're very excited because of this relation, right? You all seem very eager to see what to do with it. And this is a very bad relation, yet there is nothing to do with it. But, luckily for us, I'm going to apply a very old trick from linear algebra, just moving sides. It actually means that C XOR f of p is equal to C star XOR f of p star. And this is something I can easily work with. Take a plaintext P, apply to it f of p, XOR it with the ciphertext, and then look at collisions in this function. Instead of this, let's call this the encryption of P. This is the encryption of P star. So this slide with a twist thing allows me to find an attack in 2 to the n over 2 time and data, because I expect one such slit pair, and the slit pair automatically gives me the keys. Because if P XOR P star is actually K1. And once you have K1, you find K2 immediately. So this is a very nice attack by Ryakov and Wagner. So the thing is as follows. We have this wonderful, wonderful differential attack which meets the entire curve of the security proof, but it's chosen plaintext. And we have this very, very nice result, which is a non-plaintext, which meets one point of the security proof. And we would like to bring it together, obviously. And the solution is actually as follows. But before I go to the solution, I just want to mention the following fact. These sort of attacks, all the slide attacks, all the related key attacks that we've seen, needs something to happen. And this thing happens at the birthday bound. There is nothing to do with less data. So you need more and more data. We need somehow to bypass this restriction. And the question is how to do it. And here is the trick, the slide X. Let's assume that there is a difference delta between P and the value of the encryption of P star after the XOR with the key K. And if you work out all the details, you will find now a relation between the encryption of P and the permutation on P XOR delta with P star and P star XOR delta. Now, if you look very carefully, for every delta, this relation, if you fix delta, this relation might hold, and you can do the analysis. It's a birthday bound issue, you need that and that many pairs. It's just that at deltas you can pick arbitrarily. If you fix the amount of data, if you fix the plain texts, and you're not allowed to make more plaintext ciphertext queries, but only queries to the permutation, okay, just pick different delta values. And this is essentially the same attack up to the fact that you have the ability to generate more queries to the random permutation. And then you get the full curve and you have your analysis. Okay. I just want to quickly go over some, just mention a few references. Furuya in 2001 actually showed how to take one split pair and transform it into many split pairs. The idea is you take a split pair, and then you look at the ciphertext. The distance between them is encryption by one round. If by any chance this is the first round of the encryption, take this ciphertext and continue to encrypt them. You will get another split pair, and another, and another, and another. Very nice technique, allows way more attacks. There are actually several attacks by Orr Dunkelman that actually they're very similar to slide attacks, but they start from the middle. They assume that in DES, for example, in DES 2K, if by any chance the output of this round is 0, this round decrypts this round will decrypt this round will decrypt this round, and all the encryption collapses to a single encryption round. If by any chance the output of one of the round function is 0. Very nice trick. All the other parts of the attack are the same, and some attack is running a bit too fast. And there are several attacks several ideas on finding the split pairs using cycle structure of the permutation, because at some point, if you take Fourier's trick to the extreme, split pairs will just start to cycle. And you can use these cycles to identify the split pairs. Okay. So far, so with slide attacks. Any questions? No chance of a question at this moment, so we'll just do it very quickly. Look again at the complementation property of DES. I would like to rewrite this as the encryption of P under K, XOR the encryption of P naught under K naught equals to FFFFFFF, the hexadecimal. Does this look familiar to anyone? Let's see, this looks like key difference, this looks like a plaintext difference, this looks like a ciphertext difference. Anyone? Actually, this is related key differentials introduced by Kelsey, Schneier, and Wagner. So instead of looking at the probability of the encryption of P under the key K and P XOR some input difference, omega P and omega C, you look at differences at the key. And up to small technicalities, you can construct characteristics and differentials just like in standard differential cryptanalysis. Just need to make sure that you take into consideration that different keys might mean different subkeys. Different subkeys means that there might be something going on in the round function. So here's an example, GHOST, the Russian standard. This is a very nice facial structure, uses addition, 4 by 4 S boxes, rotation to the left by 11, and you get, I think it's 32 rounds of this form. The key length is 256 bits. The block size is 64 bits, so this is 32, this is 32. And the key schedule is very complicated. K1, K2, K3, K4, K5, K8, K1, K8, K1 to K8, K8 to K1. If it was K1 to K8, slide attacks, reflection, whatever you want. This would be a horrible idea. Having this swap here actually is a very good idea. Makes your life very, very easy. If we want security. As adversaries, it's actually a bit of hassle. So let's assume that I look at the encryption of the following form. I take all these subkeys and I flip the most significant bit. So I ask the encryption of plaintext under a key such that flip all the most significant bits. You have 8 words of 32 bits each. Please flip them the MSB. That will flip the most significant bit of all subkeys. If you flip the most significant bit of all subkeys, you may affect the most significant bit here. So to counter this effect, you also flip the most significant bit here and here. So if you look at the encryption of the plaintext P, which is P left, P right, under K, which is K1 till K8, and you look at the encryption of PL, which is PL XOR 8000, P right XOR 80000, just changing the most significant bit and flipping the most significant bit of all the subkeys. What will happen? Just like the complementation property of DES, you flip the most significant bit here, you flip the most significant bit here. This negation cancels. Sorry, there is no carry chain that might affect other bits. And you get a very simple related key differential with probability 1 for the entire cipher. Wonderful news for everyone. It can help us to speed exhaustive key search by a factor of 2. Not a great thing. If you really want to find the key, just use the difference, not most significant bit, but second most significant bit in the plaintext and the keys and everything. You get a differential characteristic with probability half per round, an iterative characteristic. For 30 rounds, it's to the minus 30. Just apply it to our attacks. I don't have to do anything at this point. It's just a single standard differential attack. I'm not going to get into the small subtleties, but there are very small ones. Most of the time, for the concept part, this doesn't really matter. And there are other related key attacks. There are many other related key attacks. Any statistical attack, any cryptanalytic attack that we have today has been transformed into a related key. Ellie mentioned for a second the possible differential attack, which is a cryptanalytic attack which assumes that uses differentials with probability 0. You can do the same with related key impossible differentials. You just construct related key differentials with probability 0. And the same goes for the boomerang attack and the linear attack and the amplified boomerang. Any cryptanalytic attack that you see today, you can publish a new paper with related key at the beginning. Lots of fun. Okay, any questions about related key attacks? Yes?
Is there any cipher that is immune to related key attacks?
Define the relations, define the meaning immune. I cannot prove to you that DES is secure. DES with 1 million rounds, I cannot prove to you that it's secure against differential cryptanalysis. I cannot do that.
No, I mean,
So I'm not. So what sort of
less than exhaustive search to operate.
even not in the related key model? I just said a single key.
No,
Let's prove that
there
this.
is not known attack which is
The,
better than
there are many ciphers with no known attacks. Take this,
even with related keys.
even with related keys. There are many ciphers like that. Serpent, for example. A great cipher. 32 rounds, no chance for related key attacks, nothing will happen there.
What is the key schedule of circuit?
It's a linear feedback shift register and then some transformation. Okay. So, as you probably noticed, we have changed a few things. For example, we decided that hash functions, well, not that important. But you cannot come to here, have a full day on cryptanalysis and symmetric cryptography, and we try to talk with you about wires and bits and running after bits and actual values and not say a single word about the AES, the Advanced Encryption Standard. I mean, at the end, besides banks, Oracle, and a few other entities, today when you go on the internet and you buy things, you're using AES for the SSL connection. On the wireless connection, it's web, and then Kenny tomorrow is going to complain a lot about web, right? You're not going to complain about web? Okay, good. Well, it depends. So, I want to present you the past, the current situation, and the future of AES, which is the Advanced Encryption Standard. So, this has many, many shortcomings. And when I say many shortcomings, it's understatement. It's inefficient in software. It was designed for hardware, but in software, it's completely inefficient. And if you go back to the 90s, people started to use this internet thing, and they wanted to encrypt, and this was not designed for CPUs. It was designed for hardware implementations. Very slow. And the key size is very limited, 56 bits. There are machines that do 56-bit exhaustive search. And the design was done by the good old guys from the NSA, which we all trust and love. And there's a problem here. And we can go on for hours. So after a lot of pressure from the cryptography community, and more precisely from the consumers of cryptography, NIST had no other choice but to start the AES competition. So they went to the cryptography community, and there were quite a lot of discussions. What should be there? For example, they increased the block size because 64-bit block, as Yehuda mentioned before, is insufficient for today's security. So 128-bit block, 128-bit key, 192-bit key, or 256-bit key. People started to think of post-quantum cryptography. Those of you who heard about quantum computers, you probably heard about the Groover search algorithm, which allows you to reduce the time complexity for exhaustive key search. If not, don't worry. It will never happen, or at least not in the next 10 years. So at the end, there was a set of rules for the competition. It started in '97, and everybody were invited to submit proposals. There was one criteria. You should be better than triple DES. Faster and more secure. So there were 21 submissions. However, everybody say always 15 because 6 of them did not meet the submission criteria, which were, at the time, implementation in assembler, implementation in ANSYS C, a written statement that you didn't add in any backdoors, which, again, okay.
How many ciphers were drawn because of that?
None. And you had to add in some documentation, and you had to compute all the internal values, and you had to support many, many, many weird things. So only 15 teams made it to the full submission pack. CAST, Krypton, DFC, E2, Frog, HPC. Now, the ones marked in red were actually broken throughout the AES process. Deal with impossible differential, Loki with differential cryptanalysis, Magenta using many, many nice tricks. I'm terribly sorry for the Hebrew. One word, I promise. Ask anyone who was in this workshop. This is Moreshet Krav. This is legacy history of how to break ciphers online. In any case, I this point, we are not going to pick anything which is broken. Then you have another 10 which are not broken, or NIST took all these 10 candidates, took the fastest 5. There was an official benchmarking machine, Pentium 2 MMX with 200 megahertz clock, etc., etc., etc. They took the 5 fastest, and they sent them to the second round. So now everybody could concentrate on these 5 ciphers. Instead of trying to break 10 candidates, you try to break 5. Instead of trying to implement in Java 15 candidates, 10 candidates, you have to implement only 5. Also in hardware, so we have Mars, we have RC6. Mars was designed by the IBM team. And from the people who brought to you DES, doesn't aspire, RC6, the RSA lab team headed by Ron Rivest, Reindal, 2 postdocs at Cal Leuven, Yehuda Lindell and Vincent Raymond, Serpent, Ross Anderson, Eli Biham, and Lars Knudsen, and Two Fish, which was designed by Counterpane, Bruce Schneier. There were measurements, there were votings, everybody tried to break each other's ciphers, sort of a Wild West going on, everybody trying to break everything. And in 2001, Reindal was selected as the advanced encryption standard, and almost immediately all the standardization bodies, ANSI, ISO, IETF, the bodies that we usually try to not think of them, but they actually control our life more than we would like to admit, very quickly adopted AES, and today it's a huge success story. It was an open process. The community could complain, complained a bit, not much, because AES was very favored. The hardware people were very happy. AES is very efficient in hardware. The implementation people are very happy. AES is very efficient. And everybody are very, very happy. And here is the cipher. It's a SP network. In a second you will see the structure. Block size 128 bits, just like I said. Key size 128, 192, 256. A small comment. Reindal is a block cipher that supports other block sizes. AES supports only 128-bit block. If you take Reindal with 128-bit block, it's called AES. And there is number of rounds which depends on the key length, 10, 12, or 14. So the more rounds, you have more mixing of the key into the state. Yes?
Was any of the finalists broken in the process?
No, and not even today. I think the best, the one with the, I wouldn't say shadiest, but the one closest to being broken is RC6. It has the smallest security margins. But the best known attack, for example, on Serpent is 12 out of 32 rounds. Mars, well, it depends how you count Mars, but it's about 20-something out of 32, but it's a weird combination. Mars is a very interesting design.
And which was the fastest?
Reindal. And I hope this will hunt you for a long time. Vincent and Yuan. In any case, this is how the cipher works. You take the plaintext, which is 128 bits, which are 16 bytes. You can do the arithmetics, but you'll have to trust me. You put them in a 4x4 matrix, and you apply the following 4 transformations. And it's amazing that you can describe the cipher. This you had many tables, and you had to remember everything. It was lots and lots of fun, right? You're all going to drink yourself to death tonight, just to remove this memory. AES is very simple. Subbytes, which is taking each of these bytes and transforming it through an 8-bit to 8-bit S-box. So one single S-box, it's the same S-box in all rounds and used 16 times in parallel. Then the shift rows operation. Shift rows operation takes the first row, doesn't change it. The second row is rotated by 1 byte to the left, the second one by 2 bytes to the left, the third one by 3 bytes to the left, or as we like to call it in Israel, 1 byte to the right. Then you take each column, 4 bytes, 32-bit value. You treat these as 4 elements of the field GF2TD8, and you multiply it by a 4x4 matrix. And that's it. do it 10 times, 12 times, or 14 times, and I completely forgot the XOR of the round subkey. Not a very important thing, but you can see that each round you XOR the subkey. One small change, the first round, before the first round there is an additional add round key operation, because otherwise the first round will make no sense. It will be a very complicated transformation, which everybody can take any plaintext and apply the transformation to the plaintext, so we didn't gain anything. And in the last round there is no mixed column operations due to symmetry in some decryption implementations. Allegedly, it has no effect on the security. So far, to the best of our knowledge, it has no effect on the full security of AES. On some reduced variants, it has an effect, but for the full AES, nobody really needs this mixed column operation. Okay, so here are the operations. Mixed column, take 4 values as elements of GF2 to the 8, multiply them by the following circular maximum separator distance matrix. Very lovely matrix. And here's the field that you need, GF2 to the 8. If you're interested, it's 11B. So, Galois field enthusiasts. The S-box, I can either give you a wonderful table of 256 elements, or I can just tell you how to compute it yourself. Take X, which is an input, an element of GF2 to the 8, define the inverse of X. Well, 0 is the inverse of itself. You will have to trust me on that. Then you write Y as a series of bits. You multiply this matrix of bits, again, circular, very nice matrix. By this vector, you add this constant vector, 63 hexadecimal, and this is the sub-byte operation, sub-bytes operations. Now, another comment. In the submission document, it's called byte sub, and in the standard, it's sub-bytes. The idea is to prevent cryptanalysis. They change also mixed column into mixed columns. I have no idea why they did that. Okay, so we have the shift rows, nothing shady there. Mixed columns you all know, add round key. I just need to tell you how these subkeys are computed. And you all look very excited and waiting to see. Yes?
I get the changes to mixed columns, so the watch engineers will understand the that
I see. Saying this is a statement of an engineer. Okay. Okay. So here's the idea. You take the key and you put it inside a matrix. Either of 4 columns, this is for AES 128, either 6 columns if you happen to have 192, or 8 columns in the case of 256. You use each time 4 new columns. So in AES 128 you use these 4 columns, then you generate from these 4 columns another 4 columns, you use them, another 4 columns. AES 192, you have 6 columns, you generate from them the next 6 columns. So these will be the first round subkey, these 2 and these 2 will be the second round, third, and 256-bit key, first subkey, second subkey, third subkey, fourth subkey. So I just need to tell you how to generate these columns. So I want to start with the easy columns, which are the second column, the third column, the fourth column. You just take this column, you XOR it with the column before it. So you do it like that. For AES 128, this ends here. For AES 192, you generate 2 more columns using this XOR method. In AES 256, there are 2 changes, and I want to go back to the first column. The first column is as follows. You take the last column, you rotate it to the left by 1 byte, so cyclically rotating it 1 byte lower. You pass this byte through the S-box, you XOR it with this column. So you still XOR the previous column with shifted version on the S-box, after S-box, of this column. So it's very similar to what we've just seen, and there is a small round constant here. Here's a table of round constants. They are the same for all versions of AES. It's just the number of round constants needed changes between AES instances. Is it sufficiently clear for the time and what you're really interested in? Okay, good. And in the case of AES 256, the fifth column is actually take one column before, apply the S-box to it with no rotations, and then XOR it with the round that comes, the column that comes from. So here it is, this is the AES, and now everybody can implement AES. If you want, you don't have to. Don't worry. It's not an exercise, though we can give this as a homework, should we? Okay, performance. AES is fast. And I'm saying really, really fast. Just to give you a comparison, if you use the AES NI instruction set, which is the new instruction set that went into Intel CPUs starting in 2009 or 10, the Westmere CPUs, and also in AMD CPUs since 2011, you can reach speeds of 3.8 cycles per byte. Now, the reason I'm using cycles per byte is because if you want to compare it with DES, saying it takes 61 cycles per one block of AES doesn't compare well with 480 cycles per DES. The block sizes are not the same. So for DES, assume something of the order of magnitude of between 40 to 60 cycles per byte if you do assembler implementation. If you happen to use counter mode, where you can do things in parallel, the encryption part in parallel, it takes 0.64 cycles per byte. It's less than the penalty of cache miss from level 2 cache. You can encrypt and decrypt faster, once the data is, of course, in the registers, faster than the time it takes to bring the data into the CPU. And I think this is fast. Now, of course, this is cheating because I have to assume that there is a counter mode and there is AES NI instruction set. Without the AES NI instruction set, you get 7.6 cycles per byte in counter mode. Not in counter mode, just multiply this number by something like 5, no, even less. Sorry, you can do around 12 with no counter mode. In hardware, if you optimize for size, 2.4 kilobytes, most of it is the state size. And you can reach speeds of speeds of 61 kilobits per second at the speed of RFID tags. This is, if I pardon my French, damn fast. This is really, really fast. If you optimize for speed, you can reach, there are cards that do more than 44 gigabits per second AES encryption. 44 gigabits per second. You can buy them off the shelf. The reason I cannot tell you some more information about them because you have to buy them and then reverse engineer and count the number of gates. They didn't publish papers. They just sell you the product. So I guess that you can do something better in your lab. And this is, for any practical purpose, sufficiently good, unless you're running a backbone or something like that. FPGAs, if you optimize for size, 222 slices and 3 blocks of RAM. On Vertex 5 of that and that brand. Who cares? And optimize for speed more than 24 gigabits per second. This is way better than this. This is way better by orders of magnitude than RSA. Some security properties, because we're all going to use it. First of all, the S-boxes are based on inversion over GF2 to the 8. This is a wonderful thing. For years, we worked on ways to generate security against differential and linear attacks. The idea is make sure that the probability of all differentials and linears is as little as possible. How do you do that? You make sure that the difference distribution table is as uniform as possible. If the difference distribution table is very low, all the values have the minimal possible entry, besides the 0 goes to 0, which is always probability 1. then the probability of any differential characteristic which has this S-box as an active S-box is limited. This inversion S-box allows us to, well, you compute the S-box, but we knew in advance that the highest entry in this difference distribution table is going to be 4, and the same goes also for linear cryptanalysis. The best properties that you can get. Moreover, the mixed column operation is an MDS matrix, which allows me to prove, well, I didn't do that, but Bar-Ilan and Vincent did it, that the number of active S-boxes in any differential characteristic for 2 rounds of AS, it's 5 active S-boxes. Each of them, the probability is at most 2 to the minus 6. In 3 rounds of AS, at least 9 active S-boxes. Best probability 2 to the minus 54. 4 rounds, you'd need at least 25 active S-boxes. The probability of any differential characteristic for 4-round AES is 2 to the minus 150. Given that the block size is 128 bits, it's okay. Now, similar statement goes for linear cryptanalysis. I'm not going to go over them. Now, you can say, okay, this is differential characteristic. Maybe they are differentials. So there were quite a lot of work ended. This line of research was ended with Liam Kellier that showed that the best differential for 4 rounds, best 4-round differential of AES has probability 2 to the minus 110. Not differential characteristic, differential. Input difference, output difference. We don't care what happens in the middle. Again, that means that if you try to do any differential or linear attack on more than 6 rounds of AES, you will need more than 2 to the 110 data. Which is decent. Okay, so just the implementation tip. When you implement AES, what you can do, look, the key schedule you compute it once, nobody cares. Shift rows is just changing the indices. So you can change the indices, you can swap the order of these 2 operations with no problem. You just shift indices. The problem is that now that you have to compute subbytes, 16 memory accesses to some table, and then apply mixed columns. A mixed column is a linear operation. So one option is to apply 16 S-boxes, and then 4 times multiplication by a 4 by 4 matrix. Another option is to use the fact that this mixed column operation is linear and to generate a combined table of subbytes and mixed columns. So if the mixed column operation was not linear operation, we need to take a huge table of 2 to the 32 values. You take any input of 2 to the 32 values here, you apply to each subbyte and then mixed columns, and you store the result in a table. However, mixed column is linear, so you can do it for each byte independently and then just XOR the results. So instead of having 16 memory accesses and then 4 multiplications by matrices, you do 1 memory access of subbytes with mixed column. You XOR the result with subbytes with mixed column, XOR the result with subbytes with mixed columns, and the result is significantly faster. So this is how you implement AES for efficiency when you don't have the AES instruction, and it's a wonderful method on 32-bit platforms. You just need some additional memory. But on most modern CPUs, we don't care about it. There is a bit of a problem in this. In the last round, there is no mixed column, so we need an additional table. Okay, so we have 5 tables. Anybody who wishes to complain? Speak now or forever hold. Well, the thing is that the table is accessed only during the last round of AES, which means that if I know to which part of the table you accessed, I know the value that you queried the table with. And this leaks information about which value you're working with. If you went to the entry which contains S of 0, the input you're holding in your hand was 0. Not very surprising. Now, Page in 2002 already said, okay, this actually means that memory access patterns, especially cache access patterns, can tell us information about the computation. And so far, both Ellie and I only spoke about attacks that go after the algorithm. But at the end, unfortunately, when we leave our ivory towers and we go into real life, in between there are security engineers and implementers. And they're very nice people, and they want to make the fastest implementation. It's just that by chance the fastest implementation leaks information about the secret computation. Now you probably heard about leakage resilience, so I'm not going to explore this side of the cryptographic world, but I will just mention the fact that there are real-life implications to how you implement things. And even though two implementation methods might result in the same speed, they might have very different security against side-channel attacks. Attacks that doesn't try to attack the algorithm, the mathematical description, but rather the implementation. Bert-Stein in 2005 worked a bit more, and then Usvik, Shamir, and Tromer showed how to actually find the key of AES using these memory access patterns. They actually implemented the attack, and there are several solutions to the problem. The first one was, let's flush the cache. So the problem is as follows. There are two processes on the machine. One of them doing the encryption, accessing tables in locations which I don't want to expose. The other one tries to find which locations were accessed. I'm not going to tell you how to do it, but it's very simple if you're sitting on the same machine, and you can also do it from the distance. There are some timing issues here. So one option is whenever you have a context switch, flush the tables, which is a wonderful idea. Then I don't know which entries the other process has approached. There's only one single problem with that. It makes everything very, very slow. Another option, the attack is as follows. So the solutions were either to flush the cache in context switch, or to just have an instruction inside the CPU. And this is what Intel and AMD decided to do. These instructions are secure against this sort of attacks. Okay, so the current state of affairs of AES security in the algorithmic sense. There are several certificational attacks. The first one was by Biryokov, Nikolic, and Chovatovich in 2009. They actually showed a related key attack given 2 to the 35 keys, meaning encryption under 2 to the 35 keys. You ask for the encryption of 2 to the 90-something values under each of these 2 to the 35 keys, and you can find the key of AES-256 in time 2 to the 131. Now we can have this discussion. Does it mean a break? Does it mean that AES should not be used? I will give a general statement, and I take no responsibility for it. As long as you're encrypting, and as long as you're doing something decent, meaning don't use any weird modes of operation, you're supposed to be okay. I take no responsibility. Not that I took any so far, but still. If you take AES-256 and you plug it into a Davis-Mayer construction, they had several nice attacks, again, because you control the key. These attacks were actually extended later, a bit later, to attacks on AES-192 and to AES-256 in the related subkey model, which is like related key, but where you have control over differences between subkeys. It's an even more stricter attack model, and you can find the key in 2 to the 99 data in time for AES-256, or 2 to the 176 data in time for AES-192, which looks a bit paradoxical. You add more key bits, you lose security, just something to do with the key scheduling. I will show you in a second these results. And recently, Bogdanov, Chovatovich, and Rechberger showed some byte-leak attacks on all 3 versions of AES. Give or take, it improves the time complexity of exhaustive search by a factor of 3 by an attack which is, it's correct, it's accurate, it works. It's just the improvement by a factor of 3 depends on your interpretation of improvements. It's a delicate issue. I don't want to get it into now. I don't have time to describe the Demirci-Selchuk attack, which is currently the best known technique against AES, which is not in these extreme cases. I just want to mention the results. The best known attack against AES-128 today is the Demirci-Selchuk type attack introduced by Derbez, Fock, and Jean in 2013 at Crypto. 7 rounds, 2 to 99, 2 to 99, 2 to 96. Data, time, and memory. Against AES-192, there is a recent attack by Wang and 2 students on 9 rounds, and there is also an attack on 9 rounds of AES-256 using this attack technique. In the standard model, these are the attacks, meaning AES-128 has 3 rounds of margin, security margin, AES-192 has 3 rounds of security margin, AES-256 has 5 rounds of security margins. So as long as you're in the single key standard approach to cryptanalysis, these are the best results. So, don't use AES in Davis-Mayer. It's a very bad idea. Please don't do that. Very, very bad idea. If you're building anything with AES, 192 or 256, it's not a PRP. Don't do anything based on its PRP-ness in your constructions, and do not assume that AES security is perfect, unless you have a good idea what you're doing there.
You mean ideal cipher, or?
It's not an ideal cipher.
PRP, it's not an ideal cipher.
It's not, even as a PRP...
Like a random key?
Yes, actually there are issues. If the key is known to the adversary, there are some statistical issues.
No, that's ideal cipher. PRP, you don't know the key.
As a permutation, yes. If you fix the key, you still might find some issues there. The best known attack in AES-128 becomes on 9 rounds. There are distinguishers on the on the PRP-ness. There are attacks. It's called. There is the theory guys presenting new ideas, and there are the practical guys trying to get publications. So we introduce crazier and crazier models. So today there is the known key model, in which you try to distinguish a block cipher with a key which was fixed and was publicly known. Notified.
So that's when we talk about PRP, that's the word ideal cipher. That's what I want to say. In the PRP situation, it's a random key that you don't know. It's just a regular...
It was picked at random. And they
but not fixed, not given.
Ah, okay.
PRP setting is not fixed.
Okay, sorry. I will take your definition. Okay. Now, I just want to show you very quickly the related key differentials for 10 rounds of AES-256. If you take a key difference of this form, and I'm terribly sorry if you happen to be colorblind, I'm terribly sorry, this is gray column, meaning this difference is in 4 bytes, the same difference in these 4 bytes, the same difference in these 4 bytes, same difference in these 4 bytes, 2 bytes. If you take this key difference and you run it through the key scheduler algorithm, you will get the evolution of this key difference, sub-key differences for 10 rounds with probability 1. So you can say, okay, so what? The key schedule is mostly linear. The thing is that if you start with an input difference, which is all gray, and the key schedule is all gray, their XOR is going to give 0 difference. 0 difference evolve to the same location. Then these 2 bytes are introduced into the state. They transformed and transformed. And this entire differential characteristic has probability 2 to the minus 56 for 8 rounds of AES. Despite the fact that I just told you that there is a proof that there are at least 25 active S boxes for 4 rounds. The idea is that the key schedule just cancels the differences. It opens up the way for many attacks. We will not discuss them because this is not the main point. Now, AES-256 is secure for encryption, but not secure in the related key model. You have to deal with it. Nothing to do about that. We hoped for, we expected, we wanted AES to be more secure against this sort of attacks, but it didn't happen. Now NIST, people ask me, so will NIST change AES? No chance. First of all, it's already out there in so many hardware implementation, and hardware you cannot easily patch. Second of all, there is no real reason to do that. There is no catastrophe coming on. These are still very theoretical attacks. And they're in very theoretical models. And there's not going to be AES-2 competition, especially now that AES has entered CPUs. You don't see Intel trying to say, okay, let's now introduce more extensions into their CPUs. Not going to happen. Is AES the last block cipher ever you're going to see?
No.
Of course not. It's on the slide. Excellent statements. First of all, we need ciphers so we could break. We need to practice. We need to work our art of running after bits, and it really helps that you have weak candidates. Feel, that Ellie mentioned earlier, is one of the best ciphers, most cited block ciphers in the history of cryptanalysis. You invent a new technique, you try to break feel. If you fail in breaking feel, the technique doesn't worth a thing. We need these toy examples. I'm exaggerating a bit. It's a wonderful, wonderful opportunity. We need these block ciphers to develop new attacks. The Demirci-Selchuk attack actually was developed for AES, but there are other attacks that were developed on other ciphers and then applied to AES. And it's very helpful to have this. When you have constrained environments, less than 2.4 kilogates, or you have very fast requirements for 8-bit machines, and there are many 8-bit machines these days, you would be amazed at their amount, or 32-bit machines, or you have different security requirements, or you need security against side channel attacks. AES is decent, but not the best engineering solution. And next week on Sunday we have a lightweight crypto day, so allow me to publish. Today is the last day for registration. If you're interested in lightweight cryptography, we have a day at the University of Haifa. Special properties, huge block sizes. If you're doing hard disk encryption, you'd be very happy with 512-bit block, 1,000-bit block, million bits block. AES is not suitable there. And there is a branch of attacks called algebraic attacks. I'm not going to enter these, but there was some time that everybody believed, or were afraid, not believed, were afraid that these attacks would actually hold against the AES. At the moment, they don't. And there is a chance that one day algebraic attacks would break AES, and then we will be in this catastrophe, and then there will be AES-2 competition. And until then, we need to have some substitutes. Research directions. At the end, this is a school designated to PhD students. Better implementations, both in software and hardware. Resistance against sidechain attacks, resistant against that, with this property, with that property. Always fun to have. Better key schedules. There was a bit of work done in that direction, trying to change the key schedule of AES such that it will be secure against all the crazy attack models. How AES interacts with other components of the system. What happens when you use AES in Davis Mayer? What happens when you use AES as a building block? There are quite a lot of things around that. Cryptanalysis, just invent new techniques and break AES. Please, break AES. And there is a question, this is a theoretical question, or a philosophical debate. Should we build our entire symmetric crypto around AES-like algorithms? You can take AES and transform it into stream ciphers, like Lex tried to do, or into hash functions, like many hash functions during the SHA-3 competition tried to do, because we have this very cool instruction at Intel, CPU. So maybe we should do that. Thank you.